All right, so Sam has purchased a $30,000 car for his business. The car depreciates 30% every year. Depreciation means the value of the car goes down by that percent each year. What will the value of the car after the fifth year be? And note the car is 0 years old when purchased, so the first year is the second entry in the sequence. Okay. Everybody has these notes out, right? This is from last week. It's not the one I gave you right now. So is this arithmetic or geometric? Yeah. Anytime you're going up or down by a percent, that's using multiplication. I was looking for that word. I don't. Well. Yeah, and see, I don't. Usually, when you talk about percents, you say of, the word of, of, like 30% of. That word of in math is used for multiplication a lot. And since we know that geometric sequences have a common ratio, you're multiplying or dividing. Yeah, this one's geometric. If you're going up or down by a constant amount, then it'd be arithmetic. Write out the sequence using blanks where appropriate. Fill in the first. Write out the sequence using blanks where appropriate. What the heck does that mean? I don't know what they mean by using blanks, but let's write it out. Okay, so based on this function, on this sequence, what does the value of the car depend on? What changes that causes the value of the car to change? What other unit do you see here other than money? Time, years, right? So, and they kind of alluded to this here in the directions. Yeah, the car was sold for 30,000, right? But how many years have passed when that car is valued at 30,000? Yeah, 0. As a matter of fact, with cars, they always say that once you drive it off the lot, you don't even have to wait a year, right? So the value will go down. It loses value right when you drive it off the lot. But, all right, so now that's the value at 0 years. They're eventually going to ask me for 5 years. So let's see if we can go up to 5. All right. So the other hint they tell you, well, if it's decreasing, see, because we're not going to state how much value the car has lost. We want to know what value it has retained, how much the car is worth. So if it's losing 30% each year, how much value is it retaining each year? Yeah, so that's the common ratio. The common ratio there is 70. You'll see that when we write out the formula. So somebody put in the calculator. So I'll do it myself also. $30,000 times 0.7. I'm getting 21,000. So after 1 year, it's gonna be worth 21,000. Somebody asked, it would have lost $9,000. Okay, but then after year 2, after a second year, times 0.7, now I'm getting that it's worth 14,700. After 3 years, times 0.7 again, now we got that it's 10,290. After 4 years, I'm getting that it's worth $7,203. And then after 5 years, it's worth $5,042.10. Now now here's the big one that I wanted you to pay attention to. This is where the word problems get tricky, right? Write an explicit formula for the sequence. Well, the way you write your explicit formula depends on what you consider to be your first amount. Since most of you consider the first amount to be what the car was purchased for, remember that the car was purchased before any time passed. Normally when we have these sequences, the first number you see counts as like the first number, but here, since the entry, like where it falls, it's dependent on years, the entry that falls under 1 is after a year has passed. So like if you go back to when I gave you these formulas, I don't remember that I told you to focus on the one on the right. That's the one that you're most of the time you're going to use, because this is when the first number you see counts as the first entry. Well, if you were to know what it was before, like if a number that came before your sequence, which in this case we are, before any time has passed, we know the number before, then you could use this one here. So if you want to use, long story short, if you want to use 30,000 as your first number, you would have to use this one here because that 30,000 is before any time has passed. If you want to use, what was the next number? 21,000 as your first number, then you could continue to use the one that we had been using before. Really the only difference is the exponent. Is whether you put n or you put n minus 1. And since you're our leader, you could decide, do you want to use the 30,000 as the first amount, or do you want to use 21? 30,000? Okay, so if n wants to use 30,000, we can say, yeah, I guess that's just the amount after some time is equal to 30,000 times, what's the common ratio? 0.7, but now just to the power of n. If you were to put 21,000, then you'd have to put n minus 1. Now they want us then to use this explicit formula to figure out what the value of the car would be after the 5th year. Remember that explicit formulas are the only ones that can be substituted into. So, now since we actually went ahead and did this manually, this is what we did up here. That when we went times 0.7 times 0.7, that's called finding it recursively. You'll see more of that in the next unit. We start comparing the differences between recursive and explicit formulas. But what we should get is what we already see there. Let's see if we get that. 30,000 times 0.7 to the 5th. Yep, and that indeed does give me $5,042.10. Did I go too fast? Does anybody need me to explain anything further? Helps to have a calculator. Let's do this last word problem. Suppose you drop a tennis ball from a height of 15 feet. After the ball hits the floor, it rebounds to 85% of its previous height. How high will the ball rebound after its third bounce, and then round to the nearest tenth? Write an explicit formula. So they want you to break this into 2 pieces. But let's do the explicit formula first. Okay. What is the height of the ball dependent on? What is the height of the ball? Last time with the car, the value of the car was dependent on time. Here, what is the height of the ball dependent on? You can't say height depends on height. After the number of bounces. Every new bounce, the ball is not going to go as high as it was before. So here now, we're not going by time, we're counting by number of bounces. So like, look, I'm not being asked to do this, but maybe it'll help you to see it. Okay, let's do it here on the side. After 0 bounces, how high is the ball? Yeah, 50. So that 15 counts as 0 because no bounces have passed. Whereas after that first bounce, okay, after one bounce, 15 times, what is it, 0.85? It will go to 12.75 feet. And then after the second bounce, you would go that times 0.85, and it will be, you're going to have to round already. So that's like 10.84 around there roughly, and so on and so forth. So when you write the formula, okay, again, the formula that you use depends on which number you want to count as your first entry, as your first height. Assuming that, like most of you see this 15, and you want to put in 15 as your first one, what's the common ratio here? Also known as the growth factor, also known as the split factor before we use those words. What's the common ratio going to be? .85. But if I use 15 as my original amount, what do I have to put for the exponent? Just the n. Because that 15 was when 0 bounces had occurred. That's before any of the bounces. Now, if they want to know how high will the ball rebound after its third bounce, that means that, yeah, all that would, if I were to keep on going on the next one, that's what I would, that's the number I would get. But since I already have a formula, instead of finding it recursively, let's find it explicitly. So let's do a sub 3. So I'm looking for is equal to 15 times 0.85 to the third. Looks like we're going to have to round this also. Tell us what it rounds? The nearest tenth. It does say in the nearest tenth. So I'm getting 9.2. Around 9.2. Any questions there before I move on? This will all be online. So now let's move on to the review page that I gave you today. You didn't get one? If not, it's going to be $5. Is this it? No, that's not it, right? This is the last one. Do I not have this? Oh. Where to put this? The number one says the font. Yeah, this is okay. I thought I had this saved, but I guess I didn't. It'll be there in a second. Oh. Okay. So they give you all the formulas that you may have to use. Let's go one by one. What is this first? Oh. What is this? What's the first one model? That formula. What does that represent? That's a growth. Yeah, that's just a regular exponential growth. What is the second one? A decay. The next one was compound interest. That's already on your notes. After that is half-life, and then finally a geometric sequence. So these first two don't say it, but this one's a growth. The only difference is if you're adding or subtracting the rate of growth or decay. All right, so let's write an exponential growth or decay model and solve it. So find the bank account balance if the account starts with $100 and has an annual rate of 4%, and the money left in the account for 12 years. That's grammatically correct. Find the balance if the account starts with and the money. Sorry, just the grammar is not making it. But let's just figure out how much they would have after 12 years. So let's do amount after. Oh, you know what? Let's write the model first. Let's do the model. So forget it with just n years. What's the initial amount here? $100. Does it say growth or decay? When you put money into the bank, do you lose money or do you gain money? Yeah, gain. So it'd be 1 plus. What is the rate? 0.04. But look, this is compounded. But it's compounded annually. So you're supposed to put the rate, which is 0.04, and divide it by the amount of times it's compounded. But annual, remember we learned just to divide by 1. Annual is once a year to the power of n times. Sorry. The amount depends on time. So this would be times 1 times t. So let's just simplify this out. This ends up being 100 times 1.04 power of t. You didn't have to write the first one. I just wanted to see how I got it. So now, how would I find the amount after 12 years? How would I find the amount after 12 years? What was that, Decay? You said put in a 12 for what? For what? Not for A, no. For T. So the amount after 12 years is equal to the 100 that we started with times 1.04 to the power of 12. Put that into the calculator. Since it's money, we should round to the nearest hundredth. Well, with money, you're supposed to round up. But if you round up, you get 160.10. But if you put 0.11, if you round up, you get 0.11. If you round to the nearest, you get. But like on something like this, if you were to put either 11 cents or 10 cents, I would take either one. 10 cents is the nearest, 11 cents is up. Money you round up. Oh, that kind of stinks, man. So after 12 years, they only made $60. Brian doesn't like that at all. Any questions there? In 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1985, how many cell phone subscribers were there in Centerville? So which type of formula are we going to use here? We're going to use growth, decay, compound interest, half-life, or geometric sequence. Yeah, this is a plain growth, yeah. So the amount after some time is equal to 285 is your original amount times 1 plus what is the rate of growth? What is the rate of growth? What is it increasing by? 0.75 to the power of how many we're measuring in years, so we'll leave it in t years, and then we'll go then and plug in how many years pass by from 85 to 94? 9 years. So a of 9 is equal to 285, 1.75. Oh, actually, you know what? Yeah, let me do this. Then you make the same mistake. Look, let me actually simplify this first. Let's make this 1.75 to the t. We had that issue on the quiz. But let's do that. If you are specifically asked to write the formula, let's write it in simplest form. And then we can put after 9 years, 285 times 1.75 power of 9. So 285 times 1.75. So after 9 years, what are we counting here? People. We're counting people. With people, how are you supposed to round? Yeah, because look, and on this one here, I have an extra 0.98637 of a person. That's not enough to have a whole person. So you're supposed to round down with people. So the amount after 9 years should be around 43,871. 43,871. That's more than 285. That's a lot. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. If we start with only 1 bacteria, which can double every hour, how many bacteria will we have by the end of 1 day? What type of a problem is this? Yeah, I would say growth, but instead of having to use a regular growth formula with 1 plus, they already give us the growth factor. What's the growth factor? It's doubling, yeah, it's 2. So the amount after some time is equal to the one that we started with. The growth factor is 2 to the power of time. Now we're measuring time by the hour. This is doubling every hour. And we want to know how much we're going to have at the end of 1 day. So what is the time going to be that I plug in? How many hours are there in a day? 24. 24. So a to the 24 is equal, I don't need the 1, it's just 2 to the 24th. And that's going to be huge. That's going to 2 to the power of 24. So the amount after 24 hours is equal to, we went from just a lonely 1 bacteria to now 16,777,216 bacteria. That's a lot of bacteria. Okay, no questions? Brian, can you take the bag off your desk, man? It'd be great if you looked this way too, but at the very least, take the bag off the desk. Please, pretty please. Didn't you want to sit there because you couldn't see from over here? Because from over there, it's still easier to see this way if you look this way. You have inherited land that was purchased for $30,000 in 1960. The value of the land increased by approximately 5% per year. What is the approximate value of the land in 2011? So what type of formula is this modeling? It's a growth, yeah. It's a growth. So the amount after some time is the 30,000 that we started with times. If it's increasing 5% per year, that'd be 1 plus 0.05. You don't have to write this. Like if you're limited with time and you're like, oh man, I don't like writing all the stuff. I hate writing. I prefer that you just write this second one. This is the more important one that you give me the growth factor in the simplest form. If you did not write this top one, but wrote the second one, fine. I can live with that. I don't have a problem with that. So then the next part of it is how much time passes from 1960 to 2011? 51 years. So the amount after 51 years is equal to 30,000 times 1.05 to the power of 51. I'm getting is money that we're measuring. So about $361,223.10. Okay, no questions, Sam? An adult takes 400 milligrams of ibuprofen each hour. The amount of ibuprofen in a person's system decreases by about 29%. How much ibuprofen is left after 6 hours? What type of situation is this modeling? This is a decay. So the amount left after T for time is equal to the 400 that we started with times 1 minus 0.29 to the power of the time. So the amount of time is equal to my decay factor here is 0.71. Since we're measuring time in hours, then it's asking me for 6 hours. The amount after 6 hours is 400 times 0.71 to the power of 6. Tell us where around, well, it doesn't. 400 times 0.71 power of 6. Around 51.24. The amount after 6 hours is around 51.24 milligrams. So we've absorbed a lot of it. Phone. Arrow. Number 6 is just another growth, so let's just skip it, and then if later on, like we have 2 days for this, if we have time, we'll come back to it. Just put like a little mark by it, so later on, if I ask you, which ones did we miss, you just let me know. We'll come back. I just want to try to have a variety. Okay, here we go. Let's just. All right, I'm gonna skip 7 also. Put a little mark by it because it's annual. I'm just trying to find some different types of formulas. 8 is the exact same one that we just did with the ibuprofen. I guess let's do number 9. A population of a certain strain of virus doubles every minute. Is that a growth or decay when something is doubling? That's a growth. Write an exponential model for the situation. All right, so the amount after some time is equal to tell us what the first amount is, so I'll just put a sub 1. It doesn't tell us. The population of a certain strain of virus doubles every minute. So it's weird. I have a feeling with the table coming up that they're expecting it to be 1. So 1 virus. Let's just make the initial amount 1. And then there's 2 to the power of the amount of time because it doubles. So make a table for the virus for the next 10 minutes. Okay, so when 0 time has passed by, when it first goes in, how much is there? How much virus is there? And then when it goes in after the first minute, 2. Then 4, then 8, then 16, then 32, then 64, then 128, then 256, then 512, then 1024. Estimate the number of virus in the host in half an hour. That would just be 2 to the 30th. A lot of virus. Shows up my screen. 7, 3, 7, 4, 1, 8, 2. Like what, 1 trillion, 73 billion. No, what's a billion? Sorry, 1 billion, 73 million, 741,120. And then approximately when will there be 500 virus in the host? Well, you could, when you're looking for time, the way to do that exactly is by knowing about an operation called a logarithm, which we've talked about before. We're not learning logarithms, so you'd have to just use like a table and estimate which one of those numbers is the closest to 500. Yeah, the 512. 512. This is like the bonus question that you have in the quiz. So approximately after 10. You want to learn about logarithms? No. Algebra 2. Interest. No, during the recent housing market collapse, decreased annually, or died. Right. Just because the wording looks a little confusing, let's just do 12. A dye is injected into the pancreas during a certain medical procedure. A physician injects 300 milliliters of dye, and a healthy pancreas will secrete 4% of the dye. See, it's just that it doesn't make sense because the word secrete, when you secrete something, it means you let out. Or maybe that's what it means, well, because they're injecting it into the pancreas, and the pancreas is taking it out. Okay. So that's what they mean by secreted. It's getting rid of. It's getting rid of 4% of the dye each minute. Write a model to predict the amount of dye remaining after 10 minutes. So this what type of model is this? It's a decay. The amount after some time. If you even want to do it, we can call it M. If we know time is being measured in minutes, we can call it minutes is equal to the original amount, which is 300 milliliters. Times 1 minus, because you're going to lose 4%. To the power of minutes. If you don't want to write that, the more important one is that you write the second one. Make sure that we know that the decay factor is 0.96. And then if they want to know 10 minutes, we can say A sub 10 is equal to 300 times 0.96 to the power of 10. So we started with 300 milliliters. It doesn't tell us where around. So predict, I'm getting 199.45, let's say 199.45 millimeters. Sounds painful. Kiara, what you doing? All right, let's do number 13. That one seems interesting. A certain bacterium is introduced into a petri dish and its population is monitored. At t equals 0 seconds, before any time has passed, 5,000 cells are present. The bacteria grow at a rate of 0.04% at 0.4% per second. Write an equation modeling the population at time t. So, population at time is equal to, what's the original amount? 5,000. Are we growing or decaying? It does use the word grow, so it's going to be 1 plus. But what am I going to add to 1? 0.004, not 0.4, 0.004. Anytime you get rid of a percent, you have to move the decimal 2 to the left. So 0.004 to the power of t, which, again, the more, you don't have to write that. If you were to even leave it out, I could live with it as long as you end up writing the more important ones. You write 1.004. Add 1 plus 0.0. Now, if you wanted to know how much bacteria there is after a minute, what would you put in for time? 60, yeah, because we're measuring time in seconds in the problem, and then went on after a minute. 1 minute is 60 seconds. So population after 60 is equal to 5,000. 0.04 to the power of 60. 5,000. And it doesn't tell us what it rounds. Not assuming that you can't have part of a bacteria. Let's just round down then. So population after 60 should be around 6353. You got it? Um, 14, I'm not gonna do the whole thing because this one would be well, here, let's just do A and B. Because the nice thing about 14 is it's already been modeled for you. But I like A and B because it makes sure you understand what goes where. Is this an example of a growth or decay? Why did okay, somebody not named Ann, tell me why is this Sam, why is that a decay? She's right. She told me it's a decay. So, but why? Somebody tell me why that's a decay. Or decay.
Because there's stuff in the parentheses that's less than 1.
Fine. The stuff in the parentheses are what you call the growth factor. The decay factor, yes, it's less than 1. It's either more important between 0 and 1. Somebody not named Hannah Marquise, tell me what is the initial mass of the, like what's the initial amount that it weighed? And it's in grams. 200. Please don't write 2009. I know that G came out of them with like a 9. 200 grams. For the last part, if you want to do it on your own, just get the 10 and put it in there because they're measuring in years. Depreciation per year. I'm looking for some compound interest ones. Per year. Oh, quarterly? Alright. Let's get to 18. Two different 18? Oh, yeah. Okay, sweet. Let's do the second number 18. Once we finish tomorrow, then we can always just recycle through these and put the ones that we didn't do. Huh? Okay. So let's just try to do some of each before we leave. Look, the first one's compounded quarterly. All right. So, if you invested $10,000 at 9% interest compounded quarterly, then how much would the investment be worth after 8 years? All right. So the amount after some time. You know what? Then this one doesn't even tell us. This one doesn't even tell us that we have to write it out. So let's just go straight into the formula, like with by plugging in the 8 years. So the amount that we'll have after 8 years is equal to, what's the initial amount? 10,000. In an investment, are you gaining money or losing money? Gaining, so it would be 1 plus the rate of growth, which is 0.09, divided by how many times it compounds. If it's compounding quarterly, what are you going to be dividing it by? Divided by 4. But then to the power of that same 4 times how much time, which is 8 years. We can clean this up a little bit. So 8 of the 8, 10,000. 0.09 divided by 5, and then to the power of 50. And then 1,000 times 1.5 power. So after 8 years, and we're counting money, which you're supposed to count, you're supposed to round up, but it's like really, really, really close to the lower one. So the amount after 8 years, 20,381. If you put 0.04, that's fine. Either 3 cents or 4 cents would be fine. If you're rounding up, it's 4 cents. Okay, let's look at the next one. You invested $1,000 at 10% interest compounded daily. Then how much would this investment be worth after 5 years? Oof. All right. So the amount after 5 years is equal to the 1,000 that you started with, 1 plus the percent, which is 0.10. If it's compounded daily, what are you dividing by? 365 in a year times the 365 times 5. Clean this up a bit. 0.1 divided by 365. Oh, that's, you know what? That's going to give me a huge decimal. Let's just put this all in the calculator. Round that right. So 1,000 times 1. 0.1 divided by 365 equals. I like to tell my calculator order of operations when it gets when there's this many steps. So first I did this in the calculator, then I'll put plus 1, then I'll put the power, that comes next in order of operations. So to the power of, and then I'll use the parentheses, 365 times 5, and then times 1,000. So after 5 years, I'm getting $1,648 and about 61 cents. It's a 5. It's a 5 for 5 years. And for the number 20, we're back at $1,000, but now, so everything is gonna look the same except for, and it's still even 10%. So we still have these two numbers are still the same, 1,000 and 10%. But now we're compounding weekly. So Samantha and Samantha only, we are taking it to 10 years. What would I divide this 0.10 by if we were compounding weekly? What was the number that we said? What is the most approximate, Samantha, most approximate number to the amount of weeks in a year? There's 7 weeks in a year. Go ahead, read. 52, yeah. Take that, Samantha. And then 52 times 10 years. It's going to be a nasty decimal too. Yeah, so let's just put everything in at once. This will be the last one for today, and then we'll pick it up tomorrow. The amount after 10 years is approximately 0.1 divided by 52 to the power of 520 times 1,000. Whoa, 0.1 divided by 52. Power 520. Why am I getting 0? Oh, because I forgot to have a 1. 0.1 power 52. 0.1 divided by 52 plus 1 power 520 times 1,000. I'm getting 2,715 point either 67 or 68 if you round it. I will finish tomorrow.